Hey there, chicken farmers. We're going to learn yet another logical proposition. This time, logical equivalence, also known as if and only if, which is written typically if with two F's, which is just pronounced if and only if. It's an extremely useful connective in logic, and it means that two things are equivalent. Now, the definition here in a module, just like we did for not, because we want to use Cox's definition, is actually quite simple. It's just the conjunction of two implications. P if and only if Q, when P implies Q and Q implies P. Think about this for a moment. That means that P and Q are in some sense equivalent. If you have P, then you can get to Q. That's the first leg of the conjunction. But then also if you have Q, you can get back to P. So proving one is sufficient to find the other. The two are equivalent. Equivalences are one of the most interesting things in mathematics because what people often find is that things stated in two radically different ways end up meaning the same thing. And that builds confidence in the abstraction, right? Something that's been useful in two different settings and then turns out to be the same idea means that, oh, that must be a worthwhile idea. It also means that, hey, one setting might be good for one kind of reasoning or one kind of application, and another setting might be good for a different kind of reasoning or a different application. And if they're equivalent, then you get to choose which mode you work in, knowing that whatever you prove in one will sort of be portable over to the other because of the equivalence, right? If you prove something about the P proposition, then you'll get to the Q world, and vice versa. If you prove something about Q, you'll be able to get back to the P world. So, if and only if is sort of a very nice result to be able to prove. It means that two things are the same in some logical sense. So, we're going to spend a bit of time on that. Throughout the course, actually, we're going to prove a number of if and only if results because they're the nice, often sort of strongest results you can get. I think of them as a complete characterization. You'll see what I mean in a bit. Let's start with just some simple workings with it. Now, here I've got our expanded proposition list where I'm noting some of the equivalences that sort of matter. I can maybe add another one here that says i.e. prop 1 implies prop 2 and prop 2 implies prop 1. Get that on another. Right? So we've seen a number of these things that are actually just kind of macros, right? Negation is really just implies false. Inequalities are just the equality implies false. And then similarly, this is just that. I'm going to list them sort of here in this list just because it's nice to keep track of that toolkit. Okay. Um, for the rest of the course, we're really going to only introduce one or two more things. We're very close to done um, coming up with new propositions, and we're getting there on being done with tactics. I get that this is a lot. This is maybe a good opportunity to take notes, and I'll have notes up for tactics um, and propositions on the website soon. Okay, let's do our first proof with this. The thing to keep in mind when you're doing a proof for something like this is that this is just sort of a macro. If we like, we could say unfold if and only if, and then it turns into this big conjunction. So it may be a little easier if I say, okay, give me P and Q first, and yeah, we'll stop there. Unfold the if and only if. Intros H. Okay, well, H is a conjunction, so we can use a pattern there. Oh, so okay, that doesn't seem so bad. Right now, it's just sort of okay. Yeah, I know how to prove these conjunctions. Oop, right? You're just breaking up the parts. Now it turns out that you can skip the middleman, right? P Q P P if and only if Q implies Q if and only if P. Just great. Let's take it, and then okay, we don't need to unfold anything. You can just remember that this is a conjunction and just say split straight away, right? And at that point, you're just working in the ordinary way. So optional exercise. We haven't done too many of these. You're going to see more of them as we get into the prover world because there's things that I think are good to do, but maybe not the most important, right? So, like, I'm trying to not assign you too much work because I know the videos are longer than they have been. So, the work of the class is shifting around. But if you have the time and you have the energy, I think these are great to do. They're going to hone your proving skill. You're going to get more confident doing proofs. And I think it's really worthwhile. But if you don't have time, I don't want you to feel bad that you can't do them. Maybe later on when we go on to practice for, say, the second midterm or something like that, these optional exercises are a great way to get extra practice if you haven't done them yet. Okay, the next part of this video, I want to show that actually we can do a bunch of nice other tactics, right? Things like rewrite and reflexivity and apply are all going to work nicely with if and only if. To do that, I want to use a running example where we're going to prove our first real if and only if lemma that's interesting, our first characterization. Let me see what it says. Okay, for all booleans b1, b2, if b1 or b2 equals true, then either b1 equals true or b2 equals true inclusively. This, I think, is a beautiful lemma, right? This lemma is completely characterizing how the OR B operation behaves. So OR B is an operation on booleans, not on proofs. But it's saying that, hey, if OR B of b1, b2 is true, then either b1 is a true boolean or b2 is a true boolean. I accidentally said holds as a, I'm sorry. So this is nice in that it lets us sort of take an OR in computation land, right? This computation on booleans, and turn it into an OR in logic land that says, hey, if this thing evaluates to true, then one of these two things needed to evaluate to true. Let's see how the proof works. It's a little laborious, and it's written. I'm going to shrink this a little bit just so things fit on screen a little better. It's a little bit laborious as proofs go. Uh, let's see how it goes. So let's follow it along. So we start out by saying, let's go by cases on just B1. You don't have to intros everything at once. So we're going to get two cases, B1 equals true, B1, B2, B1 equals true, B1 equals false. Okay. So we'll look at the B1 equals true case first. Okay. I'm going to simplify first. Watch the goal. What happened? Well, if you remember how OR is defined, if the first thing is true, you don't even have to look at the second thing. So, great. And now, looking at the goal, I'll say, okay, let B2 be given. That's fine. Let's split it up. It's an if and only if. And then I'm going to say intros underscore, which is a way of saying, yeah. There's a thing here to the left of my arrow, and I never want to hear about it again, just like in pattern matches. So notice, it just clears it, right? It just clears that implication. Now, why would I do that? Well, true equals true is not that interesting. But then also, like, look at my goal. I have to prove true equals true. That's not a big deal. Just like, yeah, go left, please. Okay, now we're in the other direction of the if and only if. We know that true equals true or b2 equals true, and we have to prove true equals true. Okay, who cares? I don't care about the premise of this conditional, of this implication. So just reflexivity. Now, we could have said h here, right? It's not going to hurt anybody to hold on to it, right? All that proof works. It's just now we have this h that we're not using. Now, maybe you could look at this and say, oh, well, let me go by cases on H and maybe I can use this. It's like, yeah, you could. But then you'll still have to deal with the B2 equals true case, and who cares? Your conclusion is easy to find. Okay. Next case. B1 equals false. Simplify again. Watch what happens on the left-hand side of this implication. Watch what happens. When I simplify, oh, the false bit just went away. Because remember, OR B is defined. If the first thing's false, you just return the second thing. Okay, let's go by cases on B2. So I'm using a destruct pattern there. So, okay, we have to split again. Now you're starting to see, oh, I see why Prof. Greenberg talked about, like, when would I ever run out of nesting? It's like, oh, proofs get nested very quickly. We're at 3 levels here. We're gonna hit 4. Okay. So we're now in the B2 equals true case. We have to prove that true equals true if and only if false equals true or true equals true. Okay, I like this one. When we're proving this one, that'll be easy. And then, okay, we'll just take that path. Okay, so we'll split because it's a conjunction. It's an if and only if. Okay, again, I'm going to intros underscore because I don't care about that true equals true right here. Right? I'm just going to say, okay, yep, intros, right, reflexivity. I could have said something different. Maybe this is more aesthetic to you. Intros, call it H, right, apply H. Okay, I don't see, cares. I mean, it's cool that you can do it that way, but it's just not that important, right? It's easy to, it doesn't really matter how you prove it so long as you're able to prove it from Cox's perspective. Humans maybe have a different attitude. Like, you might want to understand why you proved it a certain way. Okay, in the other direction, false equals true or true equals true implies true equals true. Yeah, I don't care about the premise. True is simply equal to true. Okay, now we have the contradictory case. False equals true if and only if false equals true or false equals true. What? Okay, so like we're working in a contradictory world. In one of these cases, we're going to get to blow up the world. In the other of these cases, well, there's different ways we could go. Okay, let's see what happens. So we have to prove an if and only if, so split is what we're going to do. Okay, now here we're going to name it because we want to use it. Intros H. So now we have to show that false equals true, and we have to show either false equals true or false equals true. Now here I've chosen to say discriminate H. I could go a different way. I could say left, apply H. Works just as well. So we saw this before. When you have a contradictory hypothesis and a contradictory goal, typically there's two ways you can go. You can blow up your contradictory hypothesis, or you can derive your goal from the contradiction you already have. Here they match up neatly, so either works. I think discriminate H is a little more efficacious here, a little more expeditious. Expedient, that's the word, not expeditious. Okay, now we need to show false equals true or false equals true implies false equals true. Okay, let's see which world we're in. It turns out they're the same world, and Cock really isn't smart enough to realize that, like, look, this OR is this logical OR, not the Boolean OR. This logical OR is just the same as false equals true, right? Because the two branches are the same. Okay, fine. So, which world are we in? Are we in the false equals true world on the left or the one on the right? All right, let's find out. Now, here I'll use curly braces for no particular reason. Now, we could apply H, or we could discriminate H. We'll apply H. Why not? Now, just to be clear, if we wanted to, we could do this with the double dash bullets. And then Cock will helpfully remind us in the next case that we need to do double dashes. Either way. Okay, with that proof out of the way, what I actually wanted to show you was rewriting and applying using these if and only ifs. So first, before we get there, sorry, actually not quite there, we're going to prove that OR is associative. P or Q or R is the same as P or Q or R. I'm not going to step through this. This is stuff that we've already seen before. There's nothing new. If you like, you can step through on your own. I'm happy to answer questions about it. Okay. Better layout there. Okay. So here's a version of OR be true for three things. A or B or C equals true implies A equals true or B equals true or C equals true. You'll notice I'm writing no parens and I should just be getting a left association by default. Okay. Let, rather than NMP, maybe we'll call it ABC, sorry. Let ABC be given. We need to show A or B or C equals true if and only if A equals true or B equals true or C equals true. And we could go back and we could do this kind of logic just for one level nesting more. But like, are you kidding me? Why? So what we can do is if you have an if and only if already, you can rewrite using it. Let's see what that means. What? What's changing here? We had the goal A or B or C equals true if and only if A equals true or B equals true or C equals true. When we rewrite, this turns into A or B equals true or C equals true. Why is that? Well, what we've really got here is this. No, not that. Is this. Typo. What we've really got here is that. So when we rewrite by this, Cock sees that, well, wait a minute, this is itself an OR where this is the first thing, this is the second thing. Or be true says, well, look, either this has to be equal to true or this has to be equal to true to have the whole thing be equal to true. So that rewrite gets us to there. The next rewrite will find this A or B equals true and turn it into that. And now what we have is just a slightly differently associated OR. Here we have A equals true or B equals true or C equals true. And here we have A equals true or B equals true, C equals true. So, or ASOC lets us reassociate. And now we have syntactically equal things, and we can say reflexivity. So I wanted to show this because what I'm pointing out is that you can use rewrite or be true if and only if is an if and only if. You can still rewrite by this, and Coq will just try to guess the correct direction. You can specify it, of course, if you want. Okay, apply also works for all A, B bool, A or B. So here we've chosen, this is just one direction of or be true if and only if. It's not both directions. Or be true if and only if has an if and only if here. This is just an if this, then that. But it turns out you can just apply one of these lemmas, and if it's one direction, Coq will figure it out. So we just say, what am I calling these M and M again? Sorry. We can just say, okay, we have A or B equals true. We need to show A equals true or B equals true. Or be true if and only if covers both directions of that. And here it's just applied one direction. And we can apply our hypothesis directly. Let me go back to the NM setting, just to show you that the names are not important at all here. Coq will still appropriately instantiate things, and the proof will be just fine. Okay. For all B, B if B not equal to true, if and only if B is equal to false. Okay, what might we do? Well, what have we proved before about these things? Not true is false. Seems good. Let's try it. What do we do now? Okay, there's a little bit more practice we can see. Let me apologize. These are in the wrong section of the file. I'm going to finish them here in the video and then maybe move them for future versions. Sorry about the confusion here. Okay, let's do this one. So these are just, it turns out, practice with these things. These don't belong down here with the if and only ifs. I'm really sorry. Intro is PQ. Okay, we can do a little better. HP, H not P. Okay. What are we going to do here? We know P, we know not P. We need to show Q. Ah. Let's walk through that one more time. If we know P and we know not P, what do we really know? We know P and we know P implies false. Okay, perfect. So at that point, we could say, all right, well, look, we know P implies false and we know P. We need to show Q, but who cares? Let's just show false and then we'll be able to easily apply things. This is like how the inequality worked. So we can just do the same things here. Okay. Sorry about this sort of like weird interlude. I'm sorry these are here and not further up. Totally my bad. I'll make a note on Zulip and y'all will see that. I'm really sorry. I wanted to make one final remark. You have quite a few exercises here that are worth doing. We're going to need these lemmas later, which is why I'm putting them here. They are optional. They're great practice, right? Proving these on your own will sort of let you see kind of the pattern of how you prove if and only ifs about functions. Okay, I'm going to stop here. This video went on much longer than I wanted to and got off the rails in the end. Sorry. As we continue, we're going to learn a bit more about some tactics. We are nearly done with the day. Cheers, y'all.